So this short video, we're calling it Modeling Heat Transfer and Thermal Fluid Processes with Engineering Equations Solver. Okay, so here is an outline of what we're going to cover in this short video. So first, what is the value of using software or engineering software tools to assist in performing heat transfer and thermal fluid modeling problems? And in particular, what's this engineering equation solver software? What can it do for you? It's one tool of many out there, so there are cases where it might be more helpful to use a program like MATLAB or Excel, or you can work in Python, but engineering equation solver is particularly helpful for a lot of thermal fluid type problems, as we'll illustrate here. We'll give a quick illustration of just how do you open it, what are the first things you should do when you fire up engineering equation solver, how do you do some very basic operations. Then we'll take a step back, just walk through a general recipe for how do we solve heat transfer or thermal fluid problems that we'll be using throughout the semester. And we'll wrap up with a somewhat more detailed example in engineering equation solver of using that software to solve a more complicated heat transfer problem following the procedure we're going to emphasize in the course. And at the end, we'll talk just some tips, common pitfalls, how to avoid them when you're working in engineering equation solver or other tools as well. Okay, so part one, what is the value of using software tools like the ones we're going to be demonstrating here for modeling heat transfer or thermal fluid problems? So one general observation is in working in these sorts of engineering problems, we're often going to have to manage a lot of different things at once. So potentially we'll have many different material and fluid properties that we're going to need to look up or evaluate. These may vary or depend on temperatures and pressures, which could change during the course of a calculation or at different points that we want to calculate. And if you were just to rely on tables at the back of a textbook or having to look online to find properties for every one that you might need to use, that could end up taking a lot of time and distracting you from the main problem. Also, a particular issue that we're going to often find in thermal fluid problems is that there are problem inputs in many different unit systems. So sometimes we'll have SI units, but oftentimes we'll also have information that is in English units where we're dealing with quantities in temperatures like Fahrenheit or energy units like BTUs. And again, you can spend a lot of time translating between different unit systems or flipping through textbooks to find conversion factors, which can, again, distract you from the real problem that you're interested in solving. And in particular for this heat transfer course, we're often going to encounter problems where we have nonlinear systems of equations that we have to solve. And what that means is that we've got multiple equations, we're solving them simultaneously, and they are coupled, that they have variables showing up in multiple equations. And in a lot of these cases, there's no direct solution procedure where you can just directly solve, evaluate an expression to get one variable, and then use that, plug it into the next equation, and repeat the process until you calculate all your quantities. You're often going to have to iterate on multiple variables and update multiple equations until they all balance at the same time. So you can solve equations like this in programs like MATLAB, but it's a number of steps to kind of set up a program in a way that you can use the built-in solution tools. And finally, there's often an interest once you actually have a model of a system set up or a program set up to describe some process that we'll want to look at different versions of it. So what happens for the same situation if the temperatures or heat input rates are varying? What if we want to find an optimal geometry? So we're going to vary some lengths or diameters to try to find a sweet spot. And in that case, we'll want a way of efficiently running the same program, but with slight modifications to the inputs. And this is, again, a case where the right software tool can allow you to do this final step very quickly rather than having to repeat lots of laborious calculations by hand with a calculator. And the point of this all is that as engineers, your high-level job, the reason that people would be employing you or hiring you to work on something is because they're interested in your ability to take a physical system and explain how it works or why it works and how to improve it. And if you're spending all your time distracted by how do I evaluate the various input properties or convert units or repeat lengthy calculations that a computer can do efficiently, you're not going to be able to focus on the real intellectual contribution that you can provide. You're going to be just working on the more routine operations that computers are good at. So this is the right software really allows you to focus on the interesting physical part of problems and really provide useful input to a company or for a research project or something else you're working on. Okay, so what is Engineering Equation Solver specifically? So Engineering Equation Solver, it's a software package that's really set up so that you write systems of coupled equations and it will evaluate them all simultaneously. So this is somewhat different than what other programs like MATLAB do, which are procedural programs, meaning that MATLAB will run one line of code and then the next line of code and so on. Engineering Equation Solver takes a whole block of equations and solves them simultaneously. So in addition to that feature, which is useful on its own, Engineering Equation Solver was developed by people who work in the field of heat transfer and thermal fluid energy systems. And to support that, they built in property routines for hundreds or perhaps thousands of fluids and common engineering materials. So you can access all these different material properties right away. If you want to look at how the same system would behave with two different fluids or working materials, you can just substitute which one you're evaluating the properties for. You can evaluate these properties at different temperatures and pressures and so on. So that in its own right is really a valuable resource to have in one place. Also, Engineering Equation Solver can check your units for you and do unit conversions. And after teaching heat transfer and thermal fluid courses for a number of years as a professor, I'll say that almost all of the, well, maybe 90% plus of some of the challenges I've found or some of the cases where students have really struggled working through an analysis has often been because of a unit error where, if something was listed in kilojoules instead of joules and the solution was off by a factor of 1,000, it could cause very strange issues. So that's a pretty nice tool that Engineering Equation Solver can do conversions for you, and it can make sure or give you warnings if it detects that your equations are not consistent on their units. But you have to use that feature correctly. So additionally, EES has built-in models for a lot of common situations that show up in heat transfer. So it'll have correlations for calculating pressure drop, for flow in different geometries, or heat transfer coefficients for different flow configurations, radiation view factors, a lot of other stuff that will show up. And finally, it has tools built in that allow you to generate charts, plots, parametric studies, optimization studies that will be useful once you have your program set up and you want to understand how does a system behave in different locations or over time or with varying input settings. And finally, where can you access Engineering Equation Solver? So you can get it in the Reber building if you're able to access it. It should be on the computers on the main floor of the Reber building and in the computer labs. Also, you should be able to access it over the virtual desktop interface where there's a guide for how to get there posted on Canvas. So check that out under Modules Resources. Okay, so on the previous slide, we noted that one of the unique features of Engineering Equation Solver is that it solves all equations in a program simultaneously rather than procedurally stepping through one line of code after another. And this is generally a big departure from what you might be used to in most of your prior programming or modeling courses. So why is that particularly useful in heat transfer and thermal type problems? So let's give an example of where this might show up. So let's imagine you were taking a course like a thermodynamics course and you were modeling a gas turbine power cycle or the Brayton cycle. So in this kind of system, in the simplest version of this cycle, you would have fresh air that comes into a system. You might know your inlet conditions, so you might know, let's say, an m dot, a temperature at point 1, a pressure at point 1, information like that. And if you know some information, let's say, about the compressor stage, you can plug those input properties and a few additional equations, and then you could fully define the state point coming out of that compressor at 2. And then you could take that information and let's say now you're going to model what happens in the combustion stage. So you add some heat in with some fuel. You can evaluate the combustion stage with that input, and that gets you out to point 3. And you can do a similar process to go from 3 to 4. And you've gone through the turbine and now you've completed the full cycle, and you're able to do that in a procedural sense, stepping through one component after the other. So that works in some situations, but just to think about a variation, let's talk about a so-called recuperated Brayton cycle, and this can often be a more efficient cycle. So what's going on here is in this cycle you have an additional heat exchanger, and what that heat exchanger does is it takes the exhaust exiting the turbine at 0.5 and it uses the heat from that high temperature exhaust, or relatively high temperature exhaust, to preheat the gas coming out of the compressor before you add additional heat in the combustion stage. So this can give you a much more efficient cycle because you've taken some of that heat from the from the exhaust turbine, or from the exhaust gas leaving the turbine that would otherwise just be lost to the environment, and use that and feed that back into the input of the cycle. So here's the problem, is that if I were now to model this sort of system, I could start with my analysis of the compressor as before, so I know my input state, 0.1, and I can use that to calculate my output from the compressor. But then I can't go through this heat exchanger stage right away, because to calculate from 0.2 to 0.3, I need to know how much heat is transferred from 0.5 to 6, and I don't yet know the temperature or the enthalpy or other properties of state 0.5. So in other words, to solve this system, I'm going to have to do this iteratively, where I might have to make a guess about what state 0.5 is, calculate the change in energy or the change in state from 2 to 3 based on the guessed temperature at 0.5, work my way through until I get back to 0.5, and then I'll have to complete the model, update my guess for 0.5, and then sort of iteratively solve this whole system until all of the governing equations for each step of the process are in agreement. But I can't just do this directly by stepping from the start to the end. So the nice feature of EES, after kind of discussing that illustration here, is that it does this all simultaneously for you. All you need to do are write the governing equations and sometimes make sure that you're providing reasonable starting guess values for the variables that show up in the problem. And EES is sort of the dragon that will come in and solve them all simultaneously and basically do that in a blink, rather than you having to go through the tedious process of keep updating potentially many couple of variables until all of your equations balance. Okay, so now let's take a first look at Engineering Equation Solver and see what we can do with it. Okay, so the first time you open Engineering Equation Solver, you're going to be greeted with this screen. And actually, in particular, in the first time you open it, you're going to have an extra option on the left that will let you set your unit system. And if you ever want to reset or adjust your unit system, you can do that here. So if we go to Option, Preferences, and then under that we can adjust our unit system here. I encourage you or recommend that you always work in what I'll call the base SI units. So that means we're using SI units, which are going to be meters for length. We'll work in mass in kilograms. I recommend you work in temperature in Kelvin, because you can do this calculations or the calculations for this course in Celsius. But then if you ever have a radiation problem or something where you need like an ideal gas problem, you'll often have to convert back to Kelvin anyway, so I find it safest to just work in Kelvin. And similarly, I prefer to do everything in joules, because while we often, let's say in a thermo class, will calculate enthalpies and things like that in kilojoules per kilogram, we're generally working in joules and watts for heat transfer calculations, so it'll usually just be safest to do everything in joules. And again, for the same reason, I like to do everything in the base units of Pascal. You can also make some other settings here, so I prefer to work in old school fixed space font or monospace font like Courier. I'll set my font size to be a reasonable number. You can adjust other things here. So always good to kind of get that out of the way first. Okay, so then once you've got your units and other options set, you can now start working in your actual equation window. So that's the first thing that you'll see in EES. You'll have various windows available to you at different times in a course of setting up a program. So those various windows, you can navigate between them up here. So for now, we're just in the equations window. So you can make comments in EES like in a lot of programming languages. So you can use // to make a comment for yourself for readability to start a line. So you might say this is, just the first example calculations in EES. You can also then use, there are a couple different formats available for how you set your comments. So for that first one, it'll just look black until you actually save or go to this calculations step and tell your code to check, and then it will change their comments to blue. So let's just save our program, which is something you should always do frequently. So let's just save this somewhere on this computer. So this is going to be just a first example in EES. Always a good idea to save to the cloud as well, just in case there's ever an issue with your current computer and then you lose your data if something happens. So let's just give it a name. So you can give your comments in a couple different formats. You can do / at the beginning of a line. You can have comments within quotes. So here's another comment. If you start your quote, you go quote ! You can sort of give a different colored comment, which can sometimes be useful when you're just trying to organize the different sections of a large program. And if I just hit Control Save, it will automatically do the unit or the equation check, and it'll update the coloring or the formatting of my different lines here. Okay, nothing too exciting so far. Let's actually get into some calculations. So I can set up now some equations. So let's just say I'm going to start making some variables. So let's say I have A is equal to 2, B is equal to 3.5, and I can calculate C is equal to A divided by B as an example. And now to run this program, I can go to Calculate and Solve, and I'll now get my solution window come up with all my different variables. Right now these are all dimensionless, so there's no unit problems detected. So far this looks pretty familiar to how you would write your program in any other language. Let's go back to the equation window and start changing things up a bit. So as noted before, EES solves everything simultaneously. And to convince you of that, I'm just going to move this to the beginning of my program. And now I can run it again. And EES is actually going to figure out in what sequence to evaluate different expressions, or sometimes it might have to calculate multiple equations simultaneously such that they all solve. So in other words, I can't change the value of a variable in the course of a program, like in other words, use it as one quantity at the top and then change it to be something else at the bottom. It can only have one value that it's going to try to converge to that applies throughout all the equations that I'm writing here. So now I can run this, and EES is essentially, let's see here. So I'm going to do F2, get my solution, and we get the same results because EES is solving all these at the same time, essentially, and figures out that it needs to evaluate C once it knows the values of A and B in this example. Okay, so that's kind of interesting. Another comment is that I don't need to evaluate all of my expressions in sort of the conventional format where I'm assigning a value on the left-hand side to be equal to the expression on the right-hand side. All EES tries to do is it tries to satisfy expressions or satisfy equations. So in other words, I can also calculate C by writing it as C times B equals A, and EES will iteratively, in this case, adjust the value of C until the left-hand side of this expression equals the right-hand side. So I get the same value, or I could also write it as C times B minus A equals 0, and again, EES is just trying to solve for the values of these equations that satisfy everything. And you can just sort of see what this looks like under the hood if you're curious. So if I go to the windows and I'm going to look at the computational flow window, and here's what EES is doing is, first of all, it's calculating and storing all the constants for the program. So essentially, if I ever have an equation where all it is just assigning a value to some variable, which I'll often do at the start where I have my inputs to a problem, then here what I'm going to do is just say that A equals 2, B equals 3.5, and EES is just going to do those things first. And then it's going to evaluate single unknown equations that are based on these constants. So in this case, I've got a single equation that depends on A and B, and once I know A and B, it's going to try to iteratively solve for C. Okay, so that's good so far. Let's just kind of move things around a bit, just because even though EES solves them all simultaneously, it's often easier for a human to think about these as, having a certain sequence. So these are sort of, let's say, my problem inputs. And then down here, this is going to be my, system description or system model that I'm trying to solve for. Okay, so I'll save and, just leave it like that. Okay, so now let's think about a somewhat more interesting case. So case one, we had two known variables that were our inputs, or two known parameters, and one equation and one unknown. So we knew A and B, we had one equation, and we could use that to solve for C. So let's say instead we've got B is also an unknown. B is now some different value, let's say, and we have a slightly different system model that has two equations and two unknowns. So B and C are now unknowns. So we have, let's just say our second equation is like the following: C times B squared minus A is equal to 2. So we've got two distinct equations, or two unique independent equations, and we can solve them together. So now we can run that, and we can solve for both B and C simultaneously, and we can see what that does in the computational flow window, where now we have a block, which means that there are multiple equations that have to be solved simultaneously. And you can see that what EES is doing is it's iterating on these on this block. So it had to call these equations 11 times, adjusting the values of the two unknowns C and B, until the error in the equations based on the values it was approaching are small enough. So whenever we're doing this as part of a program and we run it, before we add more code to the program, we should also make a point to update the guess values, the initial starting points for all these equations, to the current solved values. So that can improve the stability of our program, make it more likely to solve correctly, but it can also save a little time, since in the future, EES won't have to make as many iterations. Its initial guesses will be a lot closer to the most recent ones that did work. And you can also see, if you go to the options, variable info, we have the guess values for all our variables. And sometimes we can also enforce lower and upper limits for the different variables to sort of help our calculations. So for example, if we're working with, let's say, a heat transfer process that involves liquid water, we might set a lower guess for temperature to be like 274 Kelvin, or right above the freezing point. So EES doesn't try an intermediate guess in the process of calculating the program that would not correspond to a liquid state, and it would get, very weird solution values because it's calculating properties that might be like solid ice rather than liquid water. Okay, so with that general use of EES out of the way, let's now just clear this a bit and talk a little bit more about some of the heat transfer and thermal capabilities that exist here. So let's say we're working through a problem where we've got water in a system, and we need to calculate various properties of water. So let's just say, to start with, that we know our temperature. So let's just say, for example, we've got a case where the temperature of the water is 298 Kelvin, or about 25 Celsius. So here I'm going to assign this constant to have a unit that's in Kelvin. And what EES is going to do is, when we now are doing calculations that are dimensional, it will check if all of the units in an equation balance or check out correctly, and if they don't, it'll warn us that there's something probably wrong. So we've got temperature there, and let's just say, to start with, that we've got pressure is 200 kPa, or I'll write that as 200 E3 in Pascal. And then let's say now I want to calculate some properties of this water. So let's say I want to know what the density of that water is at that temperature. So what I can do is, if I know the functions, I can just plug those in right away. But also I can go to I can go to options function info, and I can then look up my thermophysical property functions. And let's say I'm interested in properties of water here, and now I want to get the density And since water is a real fluid and it's a pure substance, the way that we're thinking about it thermodynamically, it has two independent properties. You need to define the state. So here, temperature and pressure are independent. So it gives us this example way to calculate it, which here I'll just sort of use it as is. In most cases, I might need to change the name of some of those inputs, but I'm saying I'm evaluating water at some temperature is equal to T and pressure is equal to P, and I'll get the density out of this. So let's calculate that. And now I've run that program, and you can see that there is a unit problem that was detected. And the reason for this, and you can get from their explanation, is that I have this variable that I'm calling rho, and it's saying that rho doesn't have any dimensions, but we're setting rho equal to this function density that gives us outputs in kilograms per meter cubed. So really there's no problem with the program, it's just that I haven't yet set the dimensions of rho to be in the correct unit system. So here I'll just select that variable rho, and I'll say that its units should be in kilograms per meter cubed, and we're good. Also in this solution window, sometimes it's helpful to highlight different variables that are supposed to be important outputs. So we've got temperature here highlighted in yellow. So if that was something we were calculating, we'd be able to get that value. Also, sometimes helpful to have those outputs listed in sort of a second unit system that might be more familiar to us. So I can also list units here in Celsius. So that's all good. I'll just show a couple other basic things you can do in EES that are kind of good tools and tricks. So another thing I can do here is I can say that if, let's just say, for example, I had the input temperature not in Kelvin but in Celsius as the information provided to me, I still want to store that in Kelvin. So I can write here T is equal to, for temperature it's a slightly different rule. For temperature it's going to be convert temp, so I'm going to convert a value from Celsius to Kelvin, and the value would be a constant, let's say 25 Celsius. So that will convert for me the temperature to the correct value in Kelvin, and it won't have any unit problems because I'm using the built-in unit conversion factors. So convert temp is a special one. You can go between Fahrenheit, Celsius, Kelvin, Rankine. For other quantities, I can also just use regular unit conversions. So let's say, for example, or just a conversion factor, a multiplier. So let's say I knew my pressure was in PSI. So let's just say somebody told me the pressure was 30 PSI, and I want to convert that to my SI system, so I'll do 30 psi times convert from psi to Pascal. I'll get the multiplying factor. I can run this again, and you'll see here the pressure is now in Pascal with no unit problems detected. Okay, so just a couple other things to watch for. So for EES programs to work, you have to have the correct number of independent equations that is the same as the number of variables in your system. So for example, if I wasn't being careful and I had a different equation that would somehow set the value of rho to something, so let's just say, I also said that, rho was equal to the density of, air at some temperature and that pressure. I can run that. I'm going to get a warning that essentially we're resetting the value of a previously evaluated variable. So you can have that in multiple times, and sometimes if you're not careful or you make a typo or you leave out an equation, you could have a problem like this. And sometimes the error messages might look a bit different. So you just have to be careful when you're writing your program. And along these lines, you generally want to write your program in very small pieces. So just write 1 or 2 lines, run it, make sure your units check, your values are reasonable, save your program, update your guesses, and then continue working through your calculation. You don't want to try to do too much at once. Okay, so let's clear that. And one other type of error you could encounter is when you don't have enough unique equations. So like let's say, for example, rho is equal to, some factor times this density, some factor variable, we'll call it f. And here I've got 3 equations and 4 variables. So that means that somehow I had an extra variable that I didn't provide enough information to solve for. So this is just an example of some of the basic types of calculations you can do at EES. And at the basic level, EES is good for just looking up lots of different material properties and doing some basic conversions and just organizing stuff. But you could imagine that you can also do more powerful calculations that might involve modeling coupled systems of equations for pretty complex systems. Okay, now that we've covered some general ideas of how do you open up, do some basic calculations, use some of the basic features in engineering equation solver, let's start out by applying it to something that is still a very simple calculation or procedure, but is a type of thing that we'll be doing more so in this heat transfer course. So let's say we've got the following question. The situation is we're thinking about bringing a pot of water to boiling on a stove top. And how long does it take given whatever information we have and the initial conditions? So let's just sketch out this system real quick. That's always a good start before we begin writing any code or equations, is we need to look at the thing and understand what it is that we're envisioning. So let's say we've got a metal pot here, and I'll write it has some mass, and we're going to put in there some water. So we'll have M water. And what we're going to do is we're going to put this on a stovetop, and we're going to basically transfer some steady heat rate in. So we're going to call this Q in. For now, let's just make a couple assumptions that assume initially the pot and water are at some initial temperature, let's say room temperature. So we'll say that the pot plus water have initial temperature Ti is 20 Celsius, some typical room temperature value. We'll just make a couple other bits of input. So we'll say Q.in is, let's say, 300 watts, just as a guess here. The pot is, let's say, 1 kilogram, and it's stainless steel. And then the water, let's say M water, is also about 1 kilogram here. Okay, and we'll for now also add an assumption that we're going to neglect any heat transfer to the surroundings or other heat loss other than just Q in. And we're going to ignore phase change and most other stuff just to make this problem manageable. Okay, so given that, let's now make a control volume analysis here. So we'll draw a control volume that includes the pot and the water. Okay, so now let's write the energy balance for this control volume. So we have d energy in the control volume, d time is equal to the sum of any heat transfer through the boundaries. So plus or minus Q dot into the control volume, where positive is heat flow in, negative is heat flow out. We could also have work flowing in or out. So this would be W dot for the control volume, positive in or out. And we also have the potential for mass to enter or exit this control volume, which would carry some enthalpy with it. So we would say that this would be M dot, which could be in or out, times the enthalpy of those streams. So in this case, we don't have any mass flow through our system, we don't have any work, and the only Q we have entering or exiting the system is just Q dot in that we've specified. So also we can assume that the energy of the control volume can be written in a somewhat simpler way, which is that this is going to be equal to M of the pot times specific heat. We'll call it just CP of the pot for now, or CP of the metal, stainless steel, plus M of the water times specific heat of the water, times the temperature d time is just equal to Q dot of the control volume. So this is a constant here. In other words, our temperature is going to just rise linearly since we have a fixed Q dot in. So if we just rearrange this a bit, we could see that if for this to boil, assume the whole system is at a uniform temperature, it reaches 100 C. So we'll just say that if the final temperature TF is 100 C, then we could just simplify this as this whole expression as the following. TF minus TI over the time it takes. So we'll just call that T boil is equal to Q dot in over M of the pot times CP of the pot plus M of the water times CP of the water. Okay, so pretty simple problem setup here. And now what we want to do is we want to plug in all this information, write a small EES program, and use that to solve for the time it's going to take for this to boil. So now let's fire up Engineering Equation Solver and set this up. Okay, so now we've opened up Engineering Equation Solver. Let's set up this problem here and solve it out here. So I'm going to start with a blank equation window. I always like to start all of my programs with a little comment header, just so if I ever need to open them in the future, I know what they were for, when the last time I edited them was, any notes like that. So this is going to be a simple model of heating a pot of water. And I'll usually also like to put my name on this and the date. So I was working on this 2024 01/12. Okay, so usually for these sorts of programs, I'm going to start by just making a block of code that contains all of the known inputs to the problem, and that I'm usually going to put at the top just so it's a good starting point here. So this is going to be my problem inputs. So here I have the mass of my pot is 1 kilogram. The mass of water in the system is also going to be 1 kilogram. I've got my heat input rate, so that's Q in, and that we said was 300 watts. And I've got my initial temperature that we know, and that we said was 20 Celsius, but I always like working in the base SI units, so I always like using Kelvin for temperature. So I'm going to convert from Celsius to Kelvin my known input temperature of 20 C. And then similarly, I'm going to also get my final temperature of 100 C. Okay, so let's save this program. I made a mistake. It's not the convert function. I need to use the convert temp function whenever I'm working with the temperature. Okay, try that again. So save, and now let's run this. And we got our outputs here. One thing I'll just do here is I'm just going to also report my two temperatures in Celsius. That'll make it a little bit easier for me to reason about them, because it's sometimes hard to, in your head, convert between Kelvin and Celsius. Okay, so we've saved our program. We'll update our guess values for all the variables to the most recent ones, and then we'll go back to the program here. So now we need to get a few material properties, is usually a good next step. So for water, we're going to need the specific heat of water. So we'll say CP water, and we can just look this up in EES. So we can go to options, function info, thermophysical properties. We'll go down to water, and we'll get its specific heat here. And I can just plug that in. So this is a property or a function of two independent thermodynamic properties here. So for now, while specific heat does technically depend on temperature, and it does vary with temperature, I'm going to just calculate the value at the starting temperature and just use that for this problem for the sake of simplicity. So I'll say that I'm evaluating this property at Ti, and I'm also going to evaluate it at 1 atmosphere. So one convenient thing EES has for you is a bunch of built-in constants. So if we go to the list of constants under options, you can see these here. And one of them that I'll often use is the atmospheric pressure, which is valid for a lot of problems that we'll deal with unless we actually know they're happening at higher or lower pressure. So to get a constant, it ends with a hash symbol for reference. Okay, so that gives us the specific heat of water, and then we'll also need the specific heat of stainless steel. So to look that up, we'll go to Options, Function Info, and we'll go to Incompressibles, which is basically a set of data that includes a lot of common solid materials, metals. So let's go to metals from this and assume this pot is a typical stainless steel pot, which they're usually made of an alloy that's pretty similar to 304 stainless. So let's do this alloy and we'll get its specific heat. Again, we're evaluating this at some temperature, and for the incompressibles and also for some properties of ideal gases in EES, they don't actually need two independent properties. They usually just need one, which they usually like temperature as an input. So for stainless steel, this data is just really available as a function of temperature. Okay, so now we've got our material properties in. We can run this. And we'll note here that we have two potential unit problems. And the reason for that is that the two quantities here don't have units set for them yet, but they should be in a given unit system. So let's go in for those. And we know that specific heat in the base SI units should be joules per kilogram Kelvin. So we'll plug that in. Now we've got no unit problems detected, which is a good sign. So we can save this program, Control S, update our guesses, and then we can go back to the coding window. Okay, so now the last step here is we actually want to calculate our output, which was the time to reach the boiling temperature. So we worked out the calculation earlier that the time it takes is going to go as follows. So it's going to be equal to the final temperature of 100 C minus the initial one, Ti, divided by the time it takes to boil. And that's equal to the heat input rate, Q in, divided by the thermal mass of the system, or in this case, it's going to be M of the pot times the specific heat of stainless steel plus M of the water times the specific heat of water. And now we should just be able to go ahead and solve this. And even though our variable that we're trying to solve for is the boiling time, we could reorganize this to get that as on the left-hand side and all the other quantities on the right-hand side, but we can just write it in this way and let EES try to converge implicitly for the correct value of that boiling temperature. So let's run this. And we get a solution again. So we do get this unit warning again, and that's because we don't have a unit system set or specified for the boiling time. So in base SI units, that should be in seconds. And I'll also list it in hours, or maybe let's just say minutes, because that's a somewhat easier one to think about if you want to know how long it should take this water to heat up. And we could put it in a box so that it's easier to spot that if you've got a lot of different variables in your program. So here we are. It takes 20 minutes in this case, which is maybe a little bit of a long time. Maybe we need to bump up Q in, but we can do that. And hopefully that gives you an illustration of how you can use EES to do the unit conversions for you, solve your equations, which sometimes might have implicit coupled multiple equations in there, use the built-in material properties, and just generally make sure that your units and results are reasonable for thermal and fluid heat transfer type problems. Okay, so shortly we're going to use Engineering Equation Solver to work through a more complicated example problem involving heat transfer. But before we do that, I just want to take the opportunity to walk through what I'd recommend as a general process for how we approach these engineering problems that can be more open-ended and involve more steps. So important point to start with is once you have read the description of the situation and collected your inputs, you should really take the time to make a sketch of your system and really identify what are going to be the important quantities, inputs, outputs, flows, things like that you'll really want to do. And what goes along with that is really identify what is the specific question you're trying to answer. And oftentimes, if you have a really good understanding of what the question is, you can find the shortest path to an answer that doesn't necessarily involve a lot of auxiliary calculations that you don't use along the way. So once you're at that step, you can then identify clearly what information you have, what assumptions you're going to need to make to be able to solve the problem. And you can always go back and add more information here or add more assumptions if you work through the problem and you learn that you need additional more. And it's sometimes helpful to organize this information into different categories depending on how open-ended or broad the problem is. And then once we have that, we can step through the different parts of the system, apply the conservation laws or physical models until we've fully described it, and use that to solve for the unknown quantities that we're trying to answer. So as we do this step 4, which is a more open-ended one, we'll often sometimes have parts of the model or parts of the system that require information we haven't yet calculated. And a general practice I recommend is that you can use reasonable placeholder values for these quantities and make sure that as you complete your description of a system in a model or program or code, that you replace those placeholders or guesses with actual physical results based on the conservation laws or other things that you'll determine along the way. And the other important thing is that as we're setting up a program to describe a system, we're checking the results each step of the way. We're writing it in small couple lines of code at a time steps and confirming that the results from each of those have valid units, that they're intermediately reasonable, that there's no big surprises before we get to the end. If we try to write too much at once and get a solution and lots of things are really weird, it's hard to isolate what went wrong in the calculation steps, but if you can ensure that everything is reasonable as you add to the program piece by piece, you can get to a valid solution at the end, or you can identify when something goes wrong. And then the final step is to really take that information and answer the initial questions, which sometimes might take some judgment or interpretation of the results. Okay, so now let's look at an example. Let's say you've got a laptop sitting on a bed or something like that. You're watching Netflix, whatever it may be. The laptop is sitting there on a soft surface like a blanket, and as a result, some of the cooling ports are partially blocked, so the airflow can't really work its way through the laptop readily, and the laptop might heat up quite a bit as a result. So let's just say the room is at a normal room temperature value. Let's call that 22°C here, and the laptop is generating some heat, let's say 30 watts. So our question is, how hot is that laptop going to get? So let's model this system and then solve for that temperature in EES. And what I should caution is that this potentially is a real risk. So there are quite a number of fires. I know this happened to somebody I was friends with a while back, where they had left their computer running on a bed or their laptop running, and it overheated and started a fire. So this is actually a real physical problem to watch out for. So let's start by trying to make a good description of what's going on here. Okay, so to start with, let's just sketch out this system, and we're going to make it very simplified in this example. So let's say we've got the following going on. We've got the laptop, which we're going to just represent not as, sort of the open, folded open shape it might normally be, but let's just pretend it's a sort of some planar rectangular shape like this. Something kind of boring like this. It has some dimensions. We said it was 20 centimeters one way by 30 centimeters the other way, and it's pretty thin. Okay, and it is going to be at some average temperature, so let's just call this T of the device, or T of the laptop, we'll call it the device. Okay, and it's generating some heat, so we have some internal Q dot is, we said, 30 watts. And that is in a room environment. We'll call that room at some temperature T ambient of 22°C. And what's going to happen is that this laptop is going to generate that heat. That heat's got to go somewhere. If it's sitting on a blanket, it might be pretty well insulated underneath. So let's just assume that that heat has to leave the top of this rectangle to the room, and it's going to leave through two different paths. So there's going to be some convection, q dot conv, to the air, and it's probably, let's just approximate that as a natural convection process if we assume there's not too much airflow in the room. So there's going to be some natural convection to the air that's going to basically just start to flow and rise around the laptop. And then also this laptop might emit some radiation to the environment. So there could also be some q.rad to the room. And usually when you've got a situation where you've got natural convection to a air environment, the radiation heat transfer rate will typically be of significant scale or of comparable scale, usually to the convection. So that means that we probably need to account for both of these. And if we just kind of draw a control volume for this system, we could just observe that if these are all of the heat flows in the system, so there's Q generated inside the system and some heat leaving the system, then at steady state, we would conclude that our energy balance is that this Q dot of 30 watts has to equal the convection heat from the laptop to the room plus the radiation heat transfer rate from the laptop to the room. So ultimately our question is going to be, what temperature will the laptop reach, or what is the device temperature TDEV, such that the equation here will work. So in other words, as TDEV increases above the room temperature, there's going to be more convection and more radiation, and there's going to be some value that causes the sum of those two to equal the total heat that's being generated by the laptop. So next, let's just list the assumptions and any other pieces of information we're going to need to use about this system. So just to clarify, we've got no forced convection, only free convection or natural convection. We can also assume that the radiation heat transfer here is essentially the case where you've got a diffuse plus gray object or surface in a large surroundings or large enclosure. So we'll talk more about what this means later on in the heat transfer course, but for now this allows us to use a somewhat simpler result to predict the radiation heat transfer rate. We'll say that Q.rad is equal to epsilon sigma times the surface area, and let's just say the surface area here is the top face of the laptop, times the absolute temperature of the device to the fourth power minus the temperature of the surrounding room to the fourth power. Okay, and then also we're going to need a piece of information here, which is that the emissivity is some value. So let's just guess an emissivity of 0.6. So it has to be somewhere between 0 and 1, and for most real devices or most real surfaces, it's somewhere in the middle. Okay, so we're back in Engineering Equation Solver, and we're going to start stepping through the elements of this system here. So let's start as usual by putting a header in for the program. So this is going to be a model of a laptop heating up on a bed. Again, I'll put the author and date here for the program. In case I ever need to track him down, I'll know who did it. Okay, so now let's start by plugging in the known information about the system, or essentially our input quantities that we have. So these are the problem specifications. So we know the environment temperature. So this was 22 Celsius. So we'll go convert from Celsius to Kelvin, 22C. We have some geometry information about the laptop. So let's say the width of the laptop is 0.3 meters. The length of the laptop is 0.2 meters. And while it's not technically an input, this is probably a good time to also just calculate some other information. So like the surface area of the laptop, if we just treat it as a planar rectangle, it will be W times L. We can't specify the units for calculated quantities. We can only specify them for constants that we're putting in. So we're going to have to make sure when we run this program to calculate the or set the units for area to be correct. Okay, and then we have the emissivity of the device, so that we'll just call epsilon is 0.6. And for dimensionless quantities, you can also give it a unit of dash, just to make sure that you don't forget to give the units to any of the inputs you specify. And finally, we know the heat transfer rate Q, which let's call that 30 watts. Okay, so now let's run this program. We've added plenty of code, or let's save it first. So I'll save it here in this folder, and let's run it. Okay, so we get a result. All the quantities look reasonable. We just have to make sure that we've got the units sorted out for the area of the device. So let's save that, update our guesses, and now we'll go back into the code. Okay, so now we've got our problem specifications in here. We have a model for the system, which basically says that there is radiation and convection heat transfer, and we just need to make sure that those two add up to the total heat input rate. So let's just step through them one by one, and we'll start with the radiation heat transfer calculation. Okay, so we know that the heat transfer rate by radiation from the laptop to the surroundings goes as the following form. It's going to be equal to the emissivity of that laptop times sigma, the Stefan-Boltzmann constant, times the surface area of that heat for that radiation process, let's call that A of the device, times temperature of the device to the fourth minus T of the ambient to the fourth. So a problem is that I cannot yet calculate this Q because I don't know what the temperature of the device is. What we kind of have instead is that we're trying to figure out what temperature of the device causes the two different heat transfer processes, the heat transfer rate by the two processes to add up to the correct total, and we haven't even finished calculating the first one yet. So what I'm going to do is at the top of my program, maybe even above my specifications, I'm going to make a little comment block here, which is going to be my placeholder guess temperatures. And these ones are temporary. So I'm using some additional inputs here to make some guesses for temperatures that later on I'm going to remove and replace them with correct calculations. So for now, I'm going to guess that my device temperature, let's say, is a good bit warmer than the room. Not a crazy high temperature. I wouldn't normally expect that, but some temperature that's reasonably above the environment temperature. So that's like 20 degrees warmer or 15 warmer than the room temperature. Okay, so let's run this. And we'll see that for this condition, QRAD is like a little over 3 watts. That's not, it's not a big portion of the total Q. So in other words, if we know that Q radiation plus Q convection have to add up to 30 watts together, and this is a lot less than that, and we expect Q radiation and Q from natural convection to be of similar order, then that kind of suggests that for natural that the temperature will probably be a fair bit higher than 310 Kelvin, but we'll see. Okay, so our next step is to get into the natural convection heat transfer calculation. So for this, we're going to talk more later on in the course of how to do this sort of calculation, but what's going to turn out to be the case is that when you've got a rectangular shape like this, there is a dimensionless quantity called the Nusselt number, and the Nusselt number for this kind of situation for natural convection from a rectangular flat plate in a room can be approximated using a correlation, as we'll call it, which is some curve fit to data or some theoretical result, and it turns out to be a function of the Rayleigh number, which is a dimensionless group we'll work out later. So for now, let's just say that the Nusselt number is going to be equal to 0.54 times something called the Rayleigh number to the 1/4 power for this natural convection problem. And the heat transfer coefficient, we're going to call it H for convection or natural convection from that rectangular laptop to the room, is equal to that Nusselt number times the thermal conductivity of the air, so that's a material property of the air, divided by a certain length scale that shows up in this problem. So this is L for we'll just call it L for natural convection. Okay, so this will allow us to calculate the heat transfer coefficient H, but we have a couple other things we need to work out along the way. So first of all, this L for natural convection turns out to be defined the following way for this case. It's equal to the area of that rectangle divided by the perimeter. So since it's a rectangle, the area is width times L, and then the perimeter is equal to 2 times W plus 2 times L. Okay, so the Rayleigh number is defined as follows. It's equal to the speed of, or the acceleration of gravity, so that's g, or we can use the built-in EES constant g hash, which gives us 9.81 meters per second squared, times a property called beta, which is the volumetric expansion coefficient. You don't need to know this yet, but just to complete the problem, let's just kind of step this through, times the temperature difference between the surface and the air around the surface, so that's going to be T device minus T ambient, times the length scale for this process, so we'll call it length scale for natural convection cubed, divided by kinematic viscosity, so that is a material property of the air, times the thermal diffusivity of the air, which is another material property. So don't worry too much about what those material properties are, although maybe you should be familiar with the kinematic viscosity. So we're going to need to look up a few properties before we can do this calculation. So let's hop up here, and I'm going to make another block up here, which is going to be my material properties for air. Okay, so we have 3 material properties to work out. Beta for an ideal gas, the volumetric expansion coefficient, works out to be 1 divided by the temperature, or T of the air. The kinematic viscosity, nu, we can pull from the built-in functions in EES. So we'll go to thermophysical properties. Well, that's weird. There we go. For ideal gases for air. And we'll pull out the kinematic viscosity. So that depends on both temperature and pressure. So this is going to be T of the air. And we'll assume that this is happening in a regular environment, so the room, so it's at pressure P naught, atmospheric pressure. And then finally, we also need the thermal diffusivity. So let's go back and pull the thermal diffusivity. It's another material property. And this is at T ambient, and P is P naught. So this is probably way more code than we should write at once before running our program, but it would be hard to kind of write too much less than that in this case, because these variables or these expressions all depend on some earlier ones. Okay, so I made a mistake. I am short a variable. So let's see if I can track that down. I have 15 equations and 16 variables. So there's an extra piece of information here that I forgot to calculate, or an extra variable that I forgot to define, or probably had a typo somewhere. So let's do the following to try to debug that. So I'm going to basically comment out, and I can do a block comment in braces like this to hide some of the unknown quantities, or some of the equations that are probably part of the problem, and sort of work my way up until I've tracked down anything I missed. So let's run that. So in other words, when I run this, I get a solution. I'll just set my units real quick. This is in meters squared per second. This is in 1 over Kelvin. This is in also meters squared per second. And what was the last one? This length should be in meters. Okay, so now going back to our program, we'll add another line of code. So we'll add in the Rayleigh number definition. Run that. Make sure that checks out, update our guesses, save our program, then go back to the code, add in the Nusselt number, and run that. So that's good, no unit problems, all good. And then my last one is here, and I see what I did wrong. I'm using this material property of air, in my heat transfer coefficient correlation to calculate heat transfer coefficient due to natural convection, and that depends on K, which is the thermal conductivity of air, and I never specified that. So here I need to add that in. So I'll go to functions, conductivity, and I'll plug that in. So this is conductivity of air at temperature T ambient. And now our program should run. So we get to here. We have two potential unit problems. One of them is because I need to set K to be watts per meter Kelvin. And then the other one is because heat transfer coefficient H should be in watts per meter squared Kelvin. So that was what we were working to with this whole natural convection calculation, was just to work out what that heat transfer coefficient H is. And since we now know that, we can calculate Q from natural convection from the laptop to the room. So that's equal to the heat transfer coefficient H times the surface area of the device times the temperature difference T device minus T ambient. And recall that both this heat transfer rate Q for natural convection, or maybe we'll just call it QConv, and this radiation rate are assuming a arbitrary or sort of guessed temperature. They aren't based on a true temperature. So just keep that in mind, that neither of these are the correct values, but they are hopefully in the right order of magnitude. Okay, so we ran that, and we have now our Q convection is here in watts, and our Q radiation is here. And if we were doing this by hand, what we could do is recognize that the sum of these two heat transfer rates is less than the total Q, and they should be equal. And we know that Q convection and Q radiation will go up as we increase the temperature of the device. So we could just kind of keep increasing this guess value for T dev until these two add up to equal 30 watts, and we would have an answer. And EES essentially can do that for us built-in iterative solve. So instead of doing that by hand, what we'll just do is, this is our energy balance for our control volume, and that is equal to Q convection plus Q radiation is equal to the total Q generated by the laptop of 30 watts. And when we do this, we add an extra equation, but we didn't actually add any new variables. So in other words, by doing this step, we need to remove one of the variables that we already have. Otherwise, we'll have over-defined our system. And just to illustrate that, if I try running the program, we get this problem that we've basically trying to redefine a variable that was already solved for, or already had a value. So in other words, what we want to do here is we want to add this energy balance and use that to replace our guess for T device. And therefore, what we're telling the program to do, or EES to do, is to solve for the value of T device that will satisfy this energy balance for the system. So we comment out T device and run it, and we'll find that the temperature that makes this work is 338 Kelvin, or in Celsius, that's 65 C. The room is at 295 C. And that number seems high, but it also seems reasonable to me that laptops can get pretty warm. And it's possible that if you really blocked off all the airflow and the laptop was just sort of a lumped mass all at a uniform temperature, you could get up there at 65 C. So that's a solution. It's a simplified version of the problem, but this shows you how you can solve for this nonlinear system of equations. And what makes it nonlinear is that we're saying that a quantity or constant Q is equal to one term, Q radiation, which is scaling with temperature to the fourth power, and Q convection here is scaling with essentially temperature to the 5/4 power. So you can get an idea that this is going to be very hard to solve for exactly. You could never get a closed form solution for this, but you can iteratively solve for a value of temperature that makes this work. So that's sort of the basic solution. So now we've answered the problem. We know what temperature occurs here, but usually you want to know more. You want to know, for example, how does that temperature vary under different situations? What happens if Q increases, or what happens if the room temperature increases or changes? So let's just start by saying what happens if this Q here changes. And it could be lower if your laptop isn't using much power. It could be higher if you're running really high-end laptop or generating a lot of heat for whatever reason. So let's just, instead of guessing a single value, let's see what happens over a range of Q values. So what we can do in EES is remove that guess for now from our program, and we'll make a parametric table. So this is going to be what happens when we vary Q of the laptop. So let's say we're going to run it for 25 different runs. And what we'll do is we are going to look at a few different pieces of information. So let's just add in a few of these variables to the table. We don't need every single one, but I think this is probably a good starting point. So now we have this table, and we want to know basically if we change Q, how does the device temperature change, and then also how did the two different heat transfer rates change. So we looked so far at a value of Q of 30 watts. So now let's consider a range of values. So let's go from, let's say, 5 watts at the low end up to like 100 watts at the high end, and we'll just see what happens at every value along the way. So now we're going to run this same program for that whole range of values, and we can see the device temperature that occurs or that we get for each of those. So you can see that as you start getting to the high end, things are starting to get really dangerous. Your laptop would probably shut down somewhere in this range anyway, but if you had things nearby the laptop, they could melt, you could get some real issues in this case. So we have this table, we can think about that table. Sometimes it's also helpful to display this graphically so we can generate a plot from that. So let's say we're going to see how does the device temperature on the y-axis vary as a function of the heat that the laptop's generating on the x-axis. So we'll add grid lines here. We'll just make a couple settings here, and we can run this and see the laptop temperature as a function of the heat that the laptop's generating. So I'll just go in here. I have a couple preferences about how my plots look. I find the blue lines to be too distracting. I like a thick border around the table. So I think that's a little easier to look at. And this you can really go a long way with. You can add labels to this in EES. You can print out the plots. You can copy them into another program. You can overlay multiple plots if you want to. Here we can change the label here. So this is laptop power. We could call it Q in watts. We can change some of the axis limits or formats as we wish. So that's just a nice walkthrough of how you can solve a more complicated system of equations in EES. Okay, so just to wrap up this walkthrough of how to use Engineering Equation Solver for heat transfer thermal problems, I wanted to just go through a few tips and things to watch out for that are common mistakes. So if we look at this example problem that was a little bit more involved, just to highlight what we did, we solved a coupled nonlinear system of equations in the course of writing our model because we knew that the temperature was this, or the energy balance in the end, if you looked into the individual terms, had things like temperature to the 5/4 power and temperature to the 4th power, and it was a pretty funky form of a energy balance that never has a closed form solution. So we needed to solve for it iteratively or implicitly, not directly. So to get there were a couple tricks we used. An important one was that we used placeholder assumptions. So in particular, solving for that temperature, there's not a closed form value for it. We don't know the value ahead of time, but if we tried to write all of our equations down at once so that we could directly calculate it, there's a good chance something would go wrong. So it's usually good practice to start with a guess value for quantities like that, and then make sure by the end of our program we've replaced those guesses with a physical argument. So either some model to calculate some quantity that we had a guess for, or an energy balance or mass balance, or something like that. Along the way, we were looking carefully at the results that came out of our program to make sure that everything was reasonable, our units were good. We didn't try to write too much code at once, just a few lines of code at a time, because as we saw when we started writing more than a few lines of code, it became easy to make a mistake, and then a little involved to track down where we had forgotten a quantity that we needed to calculate. So don't try to write too much code at once. It makes it harder to debug your code and reason about the intermediate results. And overall, these are challenging sorts of systems to analyze. I know we applied some concepts that we haven't yet gotten to in the course, but it's also can be a little intimidating when you look at a big problem of where do you even start. And the good news is you get better with practice and experience. So hopefully you'll get some of that this semester. And just a couple things to watch out for. Make sure to correct any unit errors and warnings. I've taught enough in this whole area of heat transfer and thermal fluid stuff to know that this is the biggest pitfall. It's very easy to accidentally forget to convert a unit to the same system you're doing your other calculations in. And in this area, you can sometimes get very big errors as a result. If you have a temperature in Celsius that should be in Kelvin, you could be off by quite a bit. So again, don't write your program all at once. Only write a few lines at a time, run them, make sure that your results are plausible, and then after you've gotten a couple more lines of code in and calculated that, use the results that come out of that to update your guesses so that you aren't starting from scratch internally, which can cause your program to fail to converge. And again, check your solution at each step of the way. Make sure there aren't any sign errors, unit errors, weird output values that come in. And the last one doesn't apply as much for this course, but in particular, something you have to watch out for is that if you're ever doing a two-phase heat system, let's say you've got a process where water is going through phase change or a refrigerant is condensing, you don't know ahead of time that the fluid is single phase or two phase, and if you try to use temperature and pressure as your property input values and the fluid is in a two-phase state, those are not independent thermodynamic quantities. So it's something to watch out for. It doesn't apply so much in this case, but sometimes you have to be conscious of this and avoid those. So with that, good luck in ME 410 in your careers. Look forward to working with you over the semester. Hopefully this was a good introduction or tutorial on how to use this particular software, but also some good strategies in general for engineering problem solving.